Project 1.5 Accounting Circuit. This circuit is divided into many parts. Part 1, the button input. This part shows the difference between a pull-up resistor and a pull-down resistor. In this circuit, the pull-up resistor circuit, the electricity can flow through the 1K ohm resistor directly into the 470 ohm resistor and into the LED bulb, causing the LED bulb to light up. But when the PBNO is pressed, the electricity flowing through the 1K ohm resistor would instead flow through the PBNO and flow straight back to ground, causing the LED to dim down and not light up whatsoever. Inside a pull-down resistor, however, when the PBNO is not pressed, the electricity would flow through the orange wire, but then it would have nowhere to go because this orange wire is not connected to the 470 ohm resistor and into the ground, causing the LED bulb to not light up. But when the PBNO is pressed, the electricity can now flow through the PBNO and into the 470 ohm resistor and then into the LED bulb, causing the LED bulb to light up. Part 2, NAND gate oscillator. The NAND gate oscillator acts as a basis for this entire counting circuit. Here is a truth table for a NAND gate. Inside this NAND gate oscillator, its main components are the NAND gates, the capacitors, and the resistors. The capacitors and resistors are split into two groups, RC1 and RC2. RC1 is mainly responsible for how long the oscillation lasts for every button press, while RC2 determines how fast the square wave signal is being produced at what frequency. By switching out this capacitor right here into a bigger one, we could make the oscillation last longer for every button press, while switching out this capacitor right here could change the speed of the oscillation. Part 3, the 4017 decade counter. The 4017 decade counter is a specialty chip that can be used to count how many oscillation is being produced per press from the NAND gate oscillator. Though in this particular circuit, we're using it solely for the purpose of slowing the oscillation of this NAND gate oscillator down by 10 times. Here is the pin configuration of the 4017 decade counter. By connecting all the outputs of this particular chip into a BB10B LED bar graph, we can make this really cool pattern of the LED lights moving. Part 4, the 4510 decimal counting binary up-down counter. This is also a specialty chip that can be used to convert the slowed down oscillation signal being produced by the 4017 into actually binary counting, as seen in this footage right here. As we can see from the pin configuration of this chip, a reset button and an up-down switch can be added. By pressing this button, which is connected to this specific pin right here, the count will reset back to 0 no matter what number it is at. And by flipping this switch here, we could flip the count from counting up to counting down, and vice versa. Part 5, the 4511 binary counting decimal decoder. The purpose of this chip is to decode the signal coming from the 4510 in order to drive this 7-segment display and display the numbers in decimal form. By connecting the outputs QA to QD coming from the 4510 into the inputs A to D in the 4511 chip, but then by connecting individual resistors from outputs A to G into inputs A to G on the 7-segment display, we can display the numbers being counted in decimal or base 10 form. The reason why we'd require individual resistors for all the input and output pins of the 7-segment displays on the 4511 is because by adding these resistors, we can make the brightness of each individual LED on the 7-segment display have the same brightness. It is also to prevent overcurrent, which could cause the LED bulbs to blow up, causing the need to replace the display. Due to the existence of a carry-in and a carry-out pin on the 4510, by connecting multiple chips together and multiple 7-segment displays, we could count into numbers way past 9 and theoretically count to infinity. This is my counting circuit, and thank you very much for listening.